Welcome to the 31st lecture of graph theory. Today we will look at a new topic, namely the network flows. What is a network? It is just a directed graph. We will call it the underlying directed graph of the network N, and there are two special vertices associated with the network. One is a source, the other is a sink, say x and y. And also along with each edge or arc of the directed graph, underlying directed graph, a non-negative real value will be given. So, that means a non-negative real valued function C is defined on the edge set. So, this is the capacities. So, it can be like, for instance, we can draw a network. Let us say we mark one x and so a y. So, two vertices are special. Then we draw say two arcs here, and then so let us draw an arc here. So, directions can be like this, and say two more vertices drawn here. Like this. So, we are drawing the underlying directed graph of the network. And here there is an edge. And then we add one here, directions being this way. So, direction, opposite direction, and then two arcs here. See, here is a network. Okay. Now, the this is the underlying directed graph of the network. So, here is the source, this is the source, and this is the sink. So, you can think that some commodity is produced at x and it has to reach the market at y, and these are the routes through which the commodity has to travel or flow, transported, we can say. Then for each edge, this is a route or road or something like that. So, there is a capacity constraint. You associate a capacity function on the set of edges. That means a real non-negative value will be associated with each of the edges. Here it is. So, I am using this red color for 9 capacities and 4. So, here 3, here say 6, 1, 5 and say 1, 4 for this, and 3 for this, and 7 for this, and 3 for this, 5 for this, 5 for this, and 3 for this, 7 for this, and 2 for this, 8 for this, and 5 for this. These are the capacities. So, this together with the capacity function, this is called a network, right. So, what does it mean? A capacity means, so you try to send the commodity on a certain route, say along this edge, then it says that the rate at which, the maximum rate at which you can transport the commodity through this edge is 3 units per unit time, something like that, right. So, but in practice what actually goes through that can be less, but it can never be more if it should be feasible, right. And that is what the meaning of the capacity, right. That is like for instance, it is the capacity of that particular route along which the commodity should be transported. Not more than say 9 unit can be transported in unit time along this route, along that edge. Now, let us say what actually is a flow. A flow is defined on such a network. The flow is again a it is also a function defined on the set of arcs. So, it is a real valued function defined on the set of the network, set of edges of the network, but the only thing is it should satisfy a constraint for each vertex which is not x or y. The outgoing flow has to be equal to the incoming flow. What do I mean by that? So, for instance, if I consider a vertex here which is not x or y, x is source, y is sink, other than x and y the remaining vertices are called the intermediate vertices, we can say I, right. So, the for instance, if the vertex is like this and these are the outgoing edges and these are the incoming edges. So, the value of the flow should be such that if you add up these values, it should be equal to the value of the of flow on the outgoing edges. If you add up the values on this thing, that should be equal to the values on this. So, when we say f, that f is the real valued function which is the flow, it should satisfy f plus v means the f plus indicates the outgoing edges, the sum of the flow values on the outgoing edges. So, whenever we say a function on a set, so that means you sum up the values of the function for all the members of that set. In this case, edges are the members, and we here f plus means the members are essentially the outgoing edges of this set, and we sum up this thing. This should be equal to this one. So, for instance, these are the incoming edges. So, when you sum up this, that is f minus of e. So, yeah, f minus of this is the condition. So, you can see that this says whatever comes into this vertex should go out, right, at the rate. So, for certain rate unit time whatever comes into this vertex should go out should in unit time, right. So, that is a conservation constraint, right, because it conserves, right, whatever comes in goes out means it is a conservation condition for that this thing. So, if this condition is met for a real valued function on the network, then it is called a flow on this network. That f function f defined on the arc set is a flow. So, one should realize one should not misunderstand or misinterpret the values, the C values and the F values. In fact, the C values are associated with the network, and it is not the flow, it is only used to say that the maximum which can flow through an edge is that the capacity of that edge, but the flow is another function in fact. So, for instance, I can define the flow here as so we will say that a flow is feasible if each flow value is such that for any arc, if A is an arc, an edge, if it is non-negative, that is greater than equal to 0 and less than equal to the capacity of that arc, then it is a feasible flow. it's understandable, because when you say some commodity, so negative flow is not allowed, and also one cannot send the commodity through an edge more than its capacity. Therefore, if the flow value on a particular defined on an edge is at most the capacity of that edge and at least 0, then it is called a feasible flow. And along with this condition, conservation condition is the important thing, along with this capacity constraint, this is called capacity constraint, then it is called a feasible flow. So, we can in this network we can define a feasible flow. Say for instance, let me put it, I am using the green color to indicate the flow values here. For C this is less than 9, and here we can have say 2. So, this is less than 4, therefore, the capacity constraint, and also it is greater than equal to 0, and here I put 1, good. Here for here I put 2, and here I put 1, and these are all satisfying the constraint, like 3 is less than equal to 3 but greater than 0. Here I am putting 0, and here I am putting 0, and here I am putting 2, and so on. So, you can check whether the conservation condition is satisfied at this vertex. So, this is a vertex belongs to I, right, this is an intermediate vertex. So, here what is the flow on the incoming arcs? 4, and the flow on the outgoing arcs is essentially 2 plus 2 4, 2 plus 2 4, right. Here this is here this 2 and this 2, right. So, therefore, the constraint is satisfied for this thing. Here also we can check, for instance, this incoming is 4, outgoing is incoming is 2 and outgoing is 1 plus 1 2. So, here also it is met, and I am completing the other values here, 0 here, so it is the green, 0 here, and 3 here, and here it is 1, and here it is 6, say here it is 2, and here it is 6, and 2, and 2, and 4, right. So, you can check, for instance, here this node, is the conservation constraint satisfied, which are the incoming arcs, this one and this one, right. The total is 3 here plus 3 here and 3 here and 5 here, this is 5, sorry, 5 here, 3 plus 5 is 8. Here outgoing arcs we have 2, here is a 2, and here is a 6, already 8, and here we have only 0, right. So, therefore, 8 outgoing on the outgoing arcs, that is f minus of this particular vertex we say is equal to 8, and f plus of this particular vertex is also 8, 3 plus 5 8. So, f minus is equal to f plus here, and for all the vertices you can verify like that for all the intermediate vertices. While for x this is not true, because the only outgoing arcs are there, 4 plus 2, f plus of x is equal to 6, while f minus of x is equal to 0, because there is no incoming arc at all. What about the y? That is, we have f minus of y is equal to 2 plus 4 6, and f minus of f plus of y is equal to 0, because there is no outgoing arcs here, right. So, this is an example of a flow on this network. See, the key points are, there are two constraints that you have to satisfy. One is the conservation constraint, which is to be satisfied for all internal intermediate vertices, not on the source and sink, the other vertices, remaining vertices. So, that means whatever is coming inside into the vertex should go out. So, the sum of flow values on the incoming arc should be equal to the sum of flow values on the outgoing arc. This is one main condition, and the other condition is the capacity constraint, namely that all flow values should be non-negative, that means greater than or equal to 0, and there is a bound, upper bound on each arc, which namely the capacity of that arc. You cannot push more than the capacity of that arc. It is always so in real life, because you cannot push infinite commodity through a particular link, while of course, if there is an infinite capacity link and you can find such find a path starting directed path starting from x, and you can reach y through via a path involving only links of infinite capacity, then you can always push an infinite flow. So, but in practice that may not happen. So, usually there will be some capacities associated with any network, a real life network. So, this is the definition of the flow. Now, the next thing is to define what is a flow value. What do we mean by flow value? So, the flow value means how much we are able to, the rate at which we are able to send commodity from x to y. X is the source and y is the sink, right. From source to sink, in what rate we can send, the maximum rate at which we can send commodity through the network, right. So, this will depend on the network. Given a network along with the capacities of the edges, we can ask this question, what is the maximum flow, right. So, therefore, the value of the flow is essentially how much we can send at what is the rate at which we can send from x to w, and given a flow there is a value associated with it. For a particular flow, you know, that flow will send certain amount of commodity from x to y, that amount is supposed to be the value of the flow. How do we define it? That is the question. So, the let us say this is natural to think like that, for it is a very intuitive thing that. So, the what we sent out of x, right, is the value of the flow. So, here we are sending 4 along this thing and 2 along this thing. So, therefore, it is natural to assume that to think or define that the value of the flow is 4 plus 2 here. For instance, but then the source need not be always like this. You can have a source where, say, source x may be there may be some outgoing edges, and to the source some incoming edges also may be there. In that case, we will talk about f plus of x minus f minus of x as the value of the flow, because that is the net outgoing flow from x, Suppose we define this as a value of the flow. So, which essentially is like if you consider this x as the source, it is like the total outgoing the rate at which the commodity is going out of x, that will be the value of the flow. Now, but then is it consistent? So, it is a very interesting thing is that, so if you see y, so for instance, if you are sending x from x this much, then is it reaching y that much, the same amount is reaching y, or more is reaching or less is reaching, all these things are interesting. For instance, in y what we will be interested, what is entering y. So, for instance, there are certain edges going into y and there are certain edges going out of y. We will be interested in f minus of y minus f plus of y. This will be what enters y, the net inflow into the y. So, therefore, whatever is sent from x should reach y, right. So, we are very much interested to know whether this quantity, the net outflow from x, will be equal to the net inflow in y, right. So, we will rather prove a much more stronger statement, we will say that not only that they are equal. In fact, if you take any set, suppose you have this network with x here and y here, and then you identify a collection of vertices in the network, some vertices in the network with some connections, some connections, and this, let us say this is x. So, we have this source is inside it, y is outside it, this is v minus x, right. So, this is sorry v minus x, v minus x. So, this is, so therefore, there will be some arcs going from this side to this side, there will be something inside here. So, there will be some arcs going from here to here, and of course, you should also count the arcs which are, there are some arcs coming back also, there are some arcs which are directed backward from this x to y, right. So, some from this side to this side. So, there of course, there are several edges inside with various directions, right, various directions. Right. So, now so what will we expect? Suppose from the source the commodity is flowing into y, we would be interested in how much is the value of the flow here, what will be the value of the flow here. The what is meant by the value of flow at this cut, this point, is how much is the outgoing flow here, namely f plus of x, x minus f minus of x. So, what do I mean by f plus of x? Essentially, if this is the set x, the edges which are directed such that it is going out of x, this collection of edges is called f plus of x. In fact, the notation for is dou plus of x, but then the flow on dou plus of x is, as a short notation, we will use f plus of x. So, usually dou plus means the set of outgoing edges of x, dou minus of x means the set of incoming edges of x. Essentially, this f means the sum of the flow values on this set, and then sum of the flow values on this set will be this, and this is a short notation is given for this thing f plus, and then this is f minus x, right. So, now we are interested in f plus of x minus f minus of x. Why? Because the total outflow is that, because this much is going out and this much is coming in. So, the total outflow will be this minus this. So, what we claim is, now we claim that if you take any x such that our source belongs to that set and y does not belong to that set, that means y is in v minus x, then if we consider f plus of x minus f minus of x, this will be essentially the value of the flow that we have defined. This value of the flow we have defined, what was that? It was with respect to the source, means the net outgoing flow of the source was the value of the flow by definition. That is what we thought we should take the value of the flow to be. So, it makes sense, because not only that it is the net flow going out of the source, it is also the net flow going out of any subset of vertices containing x and not containing y. So, you can see that it is something going out of x and towards y, that is the interpretation of that. But why is this true? So, that is because you can see that if you take x and write down for x, for the source x, for the source x we have f plus of x minus f minus of x equal to value of f. By this is by definition, this is the way we have defined value of f, and then for every y element of I, we have f plus of y minus f minus of y is equal to, so maybe we should use a different notation, say for every z element of I, say z is equal to 0. Why? Because this is the intermediate node, and this is by definition of the flow, this condition should be met. This is the conservation constraint, right, and we do not have y in this thing. Y means the source, so sink is not there in this collection because in x. So, when you sum up all these equations for all, sum it for over all x element of x, for z element of x, what will happen? These inequalities are summed for all the vertices in the given collection x will happen. So, we see that these side will be this right hand side will sum up to definitely value of f, because only one of them here is non-zero, all others are zeros. So, therefore, only value of f, because see for x this is value of f, for all others because they are all from intermediate vertices, y is not there in our collection, therefore, these are going to be 0 for all others, therefore, the total here will be value of f. But when you sum up these things, what will happen? You can see that this is essentially the a collection of values here. In fact, f plus of x means all the edges which are outgoing from x, the values we are summing up the flow values on those edges, and that is what this is, right. And this is the sum of the values of the flows on the incoming edges of x. Similarly, here these are the values of on the edges which are outgoing from set, and these are the values, some of the values of the edges which are incoming to set. So, it means that if you consider any edge like this, right, suppose you consider any edge like this, some z1 z2, and suppose both the endpoints are intermediate, then what will happen? This z1 so, the z1 and z2 both are in our set, not intermediate. Suppose both x1 and x2 are in our set x, suppose this is the x and this is x, and then both of them are there. This edge will, the value here, say suppose the value of this edge, say z1 z2, say f of z1 z2 will appear in the sum for z1 as because in f plus of z1 we have this value, right, along with many other values, this will be included in that. Similarly, in the f minus of z2 along with other values, f of z1 z2 will be included, but this comes as a minus, this comes as a plus. So, this will get cancelled. So, a positive term from this and a negative term from this, therefore, they will get cancelled. So, what kind of edges will not get cancelled? The edges which are of this type, which are one endpoint here and the other endpoint outside, will not get cancelled, right. So, for instance, there are two type of such edges. One is the beginning endpoint, the start end is on inside, and the head of the arrow is on the outside, or another type is like this. So, it is coming from outside to inside, right. If these kind of edges, for instance, z1 is here, z2 is here. So, there is this z2 component, this component will not be there, therefore, this plus component will remain. So, that is these values will remain as plus, right. So, for all the outgoing edges from the entire set x, their values will remain as positive, and then on the incoming edges whatever is there, they will remain as negative. So, therefore, we will get when you sum up these kind of contributions, we will get f plus of x, and when you sum up the kind of contributions from these incoming edges, we will get f minus of x, f minus of x. So, that is exactly value of f. Value of f is the sum on the other side, right. So, this is what we get. So, we see that value of f that we have defined as the total outgoing flow from x just looking at x, that means f plus of source minus f minus of source, that is essentially the value, the total outgoing flow of any set containing the source and not containing the sink. So, by this simple argument, right, that we have now established. So, now the next stage is, because the value is defined, value of the flow is defined, and it is consistent in the sense that any cut which separates x and y, if you take the flow going through that cut, I mean from a subset x which containing the source, the net flow which is going out of that set is essentially equal to the net flow which is going out of the source. So, therefore, that is a good definition of the value of the flow, and then we are interested in maximize this value, which is which flow will achieve the maximum, because there are various given a network we can have several flow functions on the network. We want to get the flow which will maximize the value of the flow, because that will allow us to send the maximum commodity from the source to sink. So, what flow will achieve the maximum commodity? This is the maximum value. This is the next question. So, we will next show that to answer this question, we have to establish a connection between the value of the maximum flow and the value of the some of the capacities on the cuts of the network. So, given a network, we know that it is a directed graph, underlying is a directed graph, and then we can consider cuts of this underlying directed graph such that x is on one side and y is on the other side, source is on one side and sink is on the other side. Such a cut will be called a cut of the network. In fact, usually if it was a cut in the directed graph, we can even consider cuts with both x and y on the same side, the source and sink on the same side, but we will not consider such cuts for in the case of the networks. Therefore, whenever we say cut in the network, we mean source is on one side of the cut and the sink is on the other side of the cut. So, x belongs to one side x and then y belongs to v minus x. This is the meaning of that. Now, what is the capacity of such a cut? Essentially, the capacity of the cut means if this is the cut. So, x is here, source is here, and then these are the outgoing edges. The capacity of the cut means the sum of the capacities of the outgoing edges. So, for instance, C of this edge, C of this edge, C of this edge, C of this edge. If you sum up these capacities, this capacity, this is the sum of the capacity, this is the capacity of the cut. There are incoming edges, they do not contribute to the capacity of the cut, right. The incoming edges like this will not contribute to the capacity of the cut. When you say capacity of the cut, we are just considering the outgoing edges. So, remember, when I say outgoing, we are considering the cut as the part containing the source and outgoing from that, the source side to the sink side, that is the direction. And the first and easy observation that we can make is that any flow, if it is a feasible flow, has to have value less than equal to capacity of any cut. You can take any cut in the network with source on one side and sink on the other side of case, then the capacity of that cut will be an upper bound for the value of the flow, whichever is the flow, otherwise it cannot be a feasible flow. Why is it so? It is easy to see, because we have already seen that the value given x, suppose x is a cut, then the value of the flow is equal to f plus of x minus f minus of x, and this is what? This is essentially the flow values on the outgoing edges from x, and each flow value has to be less than equal to the capacity of that outgoing edge. Therefore, this is definitely less than equal to the C plus of x, that means the sum of the capacities on those outgoing edges of x, and of course this is minus what, of course we can, when it is smaller and smaller, this quantity, this entire quantity can become bigger. So, but how small can this go? Of course, in the worst case they can, it can go to 0, because you know the 0 is a lower bound for any flow value. Therefore, this is minus 0, therefore, this is less than equal to C plus of x, and this is exactly the capacity of this cut, right, the x V minus x cut. So, therefore, this is the value of the flow can be at most the capacity of the cut. But then one will ask, okay, can, this is an inequality, value of the flow for any flow is less than equal to the capacity of any cut, but can it be ever be equal? First, if you carefully look at this thing, you can easily see that if it is equal, then this has to be 0 and this has to be equal to C plus of x, otherwise how can it be equal, because in both cases here also it should achieve the maximum possible, here it should achieve the minimum possible. That means, if the value of f is actually equal to the capacity of that cut, then we know that each flow value on each outgoing arc has to be equal to the capacity of that arc, which means in our terminology we will say that each arc has to be saturated there. Saturated means it achieved the maximum capacity possible on that arc, right. The flow, that is the flow on that particular arc edge is exactly equal to the capacity, the maximum possible, right. Then it is equal to the capacity, it is so that arc has to be saturated with this flow. So, otherwise even one arc is not saturated, it will, the sum will not become equal to the capacity of will be totally equal to C plus of x, right. Similarly, for every incoming arc we should have 0 capacity, right, we should have 0 flow value, because if it is little more than 0 there will be a reduction here, and then how can it be C plus x. So, the equality is achieved only if all the outgoing arcs are saturated by the flow and the incoming arcs are 0, have 0 value on that, it is a 0 flow on those arcs, right. That is the only way you can achieve the this thing. So, now suppose a flow is such that this condition is met, that means the flow is such that its value is equal to the capacity of a particular cut x, then we can immediately say that it is a maximum flow. Why is it so? And not only that, it is a maximum flow, and among all the possible cuts of the network, what we have now located is a minimum cut. Why is it so? Because see, this is the cut where we have seen the equality, and then say f is the flow such that f of x, right, the flow f plus of x minus f minus of x is equal to C plus of x. Suppose it happened, this is, remember, this is the value of the flow, right. Now, anyway, suppose f star is the flow which achieves the maximum, right. So, one will ask, will there be a flow which achieves the maximum, right, of course, but see, if it is, as I mentioned before, if there is an infinite sequence of arcs, so a directed path which all infinite are, it can be infinite, because, but in general let us assume that all the capacities are finite, and then there is a maximum flow that can be achieved. So, there is a maximum flow, suppose. So, then let f star be that maximum flow, then value of f has to be less than equal to value of f star, because that is the definition of the maximum flow, right. And then we can see that this f star also being a flow has to satisfy the property that it is less than equal to the capacity of the cut C plus of that cut. So, C plus of that particular cut, say let us say let us call it the cut as x is the cut, let us say the L for this cut alone we can give a name cut, and this let us say capacity of the cut, and then this has to be so the capacity of the minimum cut, and this has to be less than equal to capacity of this particular cut, right, capacity of the because the minimum cut is anyway less than equal to this thing. But then we know that suppose we assume that this and this is equal, value of the flow is equal to the capacity of this cut, then it means that this and this also are equal, and this is also equal, this is also equal, everything is equal. That means this is a maximum flow and this is a minimum cut, that is the meaning of that. So, our inference is that in somehow if we can observe a flow such that its value is equal to the capacity of the cut, then that particular cut has to be a minimum cut, and the flow which I have obtained now is a maximum flow, that we have indeed located a maximum flow. So, that is a very interesting observation, useful observation, because if you are looking for a maximum flow and we want to get a maximum flow, this is the way to identify that okay, we have indeed obtained a maximum flow. That means to identify some cut such that that cut is saturated by this flow, and not only that, how do we identify that it is in fact saturated? So, all the outgoing arcs has to be saturated, also all the incoming edges has to be of 0 value. This is the only way you can achieve the maximum saturate that cut, because you know the otherwise if there is any non-zero value on the incoming edge, the value of the flow will be less than C plus of x, right, because C plus of x minus something. While on the other hand if any outgoing edge was unsaturated, then how can the value of the flow f plus of x minus f minus of x be equal to C plus of x, right. So, you cannot achieve that. So, every outgoing edge is saturated and also every incoming edge is 0, right, 0 value of flow on that incoming edge. So, in such a situation only the minimum that cut will be the value of the flow will be equal to that cut, and then we are sure that here what we have observed is a maximum flow and this cut is indeed a minimum cut. This is the key observation. Now, the next question is so should it happen, right. So, we know that the maximum flow has to be less than equal to the minimum cut, that is very clear, because as we have seen the flow value is f plus of x minus f minus of x, and it can never be above C plus of x, right, the value of the cut. That is very clear, but can it ever achieve for a given network? Is it guaranteed that you can reach that? So, the next theorem will assert that it can always be achieved, and in fact there exists a flow, there is always a flow in a given network whose value is equal to the value of the minimum cut. This is the next statement. This is called the max flow min cut theorem. How do we prove this thing? So, to prove this thing, this is the idea. So, we have to define, so suppose you are given a flow. Now, if it is not the maximum flow, we will show how we can increase the value of the flow by a small technique. It is a simple idea. So, it is essentially if you are given a flow, then what we are going to do is to show a method by which we can increase the value of the flow. For instance, say look at say I am just taking this is the source. Suppose you have a sequence of these arcs here, some other arcs also can be there, but you just identified this set of arcs, right. This is a path from x to y, and it so happens that suppose there is this arc has capacities C1, but the flow value is some F1 less than C1, that means strictly less than C1, that means it is not full here. On the other hand, and this here the flow value is not 0, it is more than 0, right, more than 0, and here the flow value is less than the capacity here, right, and here the flow value is again less than the capacity. So, what we are thinking is to find out a path starting from x to y, sometimes containing forward edges, sometimes containing backward edges is a backward edge, but which gives us some possibility of increasing the flow. How does we formally we will define like this. So, we will consider if all the forward edges has in this path has to be unsaturated, right, forward edges has to be unsaturated. So, that something more can be pushed through that edge, that means it is not equal to the capacity even now, there is some difference. So, this difference for an edge, for a given edge A, so this f of C of A minus f of A will be defined as the epsilon of that A, that what is left on that edge, what more can be pushed through that edge. On the other hand, if it is a backward arc on this path, then we will take it as the value of the flow f of A itself, that is the epsilon of A, which essentially means that we can cancel that flow and go forward, that is intuitively that is the meaning of that, but that is why we want this to be greater than 0. So, it should not be a 0 flow. So, now we will generally define a x path starting from the source x. So, a path is a unsaturated path if it is composed of edges, if it consists of edges which is not yet saturated in the sense that if it is a forward edge, it has not achieved the capacity fully, and if it is a backward edge, the 0 value of the flow is not 0, it is a little more than 0, right, with respect to the path. If it is a backward edge, then the flow value has to be little more than 0, that means it should not be, it will not cross the capacity, but it will be more than 0. So, that we can cancel the flow and go forward, and if it is a forward edge, it should be less than the capacity, so that we can push further, and the epsilon of that path, this particular path will be defined as the minimum of the epsilons of the edges over this path. Over all the edges of the path, we will take the value of that. If it is a forward edge, this value of the epsilon is what is left, that means capacity of A minus the flow value of A, the value of A, flow of A, flow value on the A, and if it is a backward edge, it is just the flow value of A, because it is what we are thinking is to reduce the flow there, right. So, that should be non-zero, right. So, this if this epsilon is non-zero, then we will say that it is an unsaturated path, and if you have an unsaturated path starting from x and reaching all the way to y, then that is an incrementing path, because we can push some flow through that and to all the way to y, right. So, why do we think that we can push a flow? What does it mean? It means that suppose this epsilon quantity we increase, so on any forward edge on this path, if we increase the flow by this epsilon quantity, the capacity constraint is still satisfied, because we can indeed increment, because that epsilon was the minimum over what was left, the difference of the C A minus F A for all the arcs A which are in the forward direction in that path. So, we can always increase by that quantity in this path, and also whenever we had the reverse arc, we rather decrease the value, decrease that flow value. The claim is the flow condition is not. So, after doing this thing, whatever new flow we get f dash is obtained from f by doing this operation on the set of arcs, and all the other arcs whatever flow value is there, we will keep it unchanged. Then you can see that, for instance, if you what change have you done here in this kind of a, in say for instance in this kind of a situation where there is a forward arc coming in and forward arc going in. So, then you see f minus is increased a little bit, but f plus is also increased a little bit, some incoming edge got an increment. So, an outgoing edge also got the same increment. Therefore, f plus will remain equal to f minus for that particular vertex, right. So, therefore, the conservation constraint will not be lost, and also capacity constraint we were careful not to violate. Similarly, in a place like this, for instance, if you look at a vertex like this is an outgoing edge and this is an incoming edge. Here we are incrementing the value on this, but decreasing the value on this. Both are outgoing edges here. So, f plus got an increment due to this, but then a decrement it was decreased due to this edge. So, f plus is unchanged because at the f minus there is no change at all. So, you see both are outgoing edges. So, there is a we increase this and we decrease it because there this reverse direction, therefore, our flow value was reduced by epsilon, right here. So, therefore, this here also the conservation is not lost because earlier it was f was satisfying the constraint. So, if we construct a flow f dash like this, it will still again be a flow, and not only that, it has increased value. Why is it so? Because if you look at x, if you look at the x, this edge, as far as this edge is concerned, it has got an increment or increment if it is an outgoing edge. If it is an incoming edge, then what will happen? So, that is reduced there. So, overall f plus of x minus f minus of x will increase, this flow value is this, right, because if it was in the opposite direction, this quantity got a reduction, and therefore, the overall value will increase, or if it is in the forward direction, this quantity will increase. Therefore, f plus of x minus f minus of x will anyway increase. So, the flow value, the overall flow value will be more. So, value of f dash will be equal to value of f plus the epsilon of p that we are where p is the incrementing path that we have selected. So, this is how we can increase the flow value. So, we can keep on doing this as long as we can do that. So, when can we do this thing? If we can find an incrementing path, we can do that, or in other words, starting from x, we can, if we can search through the saturated paths, unsaturated paths and reach y, and then if even if one path is obtained like that, an unsaturated path is obtained using sometimes using forward and backward edges, sometimes it does not matter, our definition includes both kind of. So, because if it is backward edge, we are planning to reduce the flow there, if it is a forward edge, we are planning to increase the flow there. So, if it is a backward edge, then it should be a non-zero value there currently, if it is a forward edge, it should be a value which is strictly less than the capacity of that edge. Therefore, as long as we can find one incrementing path starting from x and reaching y, then we can increase the flow value. So, we keep on doing this, we reach a situation where we cannot do it further. So, suppose it is it stops. So, when does it stop? Because we are unable to find any incrementing path starting from x. So, what we can do is we can start from x and collect all the vertices which can be reached by traversing via some paths which are unsaturated. So, we collect all the vertices like that starting from x, right. Of course, it is very obvious that we cannot reach y is outside y, and a collection of vertices maybe are outside. So, we naturally see that there is a cut here. The cut means this x means the vertices which are reachable from the source via unsaturated paths, right. Up to here I can reach, and so due to some reason I cannot go further, and that is why we cannot reach y. There we definitely define a cut. This cut will have this following property. So, we are claiming that this cut is already a minimum cut, or in fact the current flow is actually with respect to a flow only we are doing this thing. Actually, if there is no incrementing path from x to y, then it is already a maximum flow, and this cut we have got is actually a minimum cut. This will give us evidence that it is a maximum flow. Why is it so? When you inspect the edges, forward edges, why can't I go forward from somewhere here? Because that is because there is a forward edge, and I can reach up to here by an unsaturated path. Why can't you go here and capture this guy also? That is because the capacity of this edge is equal to the flow value on this edge. That is why we cannot push further flow on that. Therefore, this is a saturated edge. Each of these forward edges has to be saturated edges, otherwise I could have captured one more vertices that we have captured all possible vertices which can be reached from x via a saturated path is not unsaturated path is not correct if any of these edges were unsaturated. So, all the forward edges are saturated here, and also all the reverse edges have 0 flow, because if it is even one was non-zero, then we could have captured the if there was a flow edge like this with a non-zero greater than 0 value on this, then we could have captured this vertices also as a vertex which can be reached from x via an unsaturated path. So, we know that all these backward reverse edges incoming edges of x, this set is non-zero, and all the edges which are outgoing from x are saturated. Therefore, as we have seen, this flow has kind of saturated this cut. So, the value of the flow is equal to the value of the cut here, C plus is equal to that f plus of x minus f minus of x, as you have seen, and therefore, it has to be a minimum cut and the flow has to be a maximum flow. So, we indeed have reached a maximum flow by doing this thing. So, remember what we have done is to start with say a 0 flow or something, start pushing flow through an incrementing path, increasing it. So, f is made f dash is made f double dash, like that we keep on incrementing the value of the flow until we cannot do it further. Why can't we do it further? Because we are unable to find any more incrementing paths in the network. So, in this case we have shown that. So, if you collect the set of vertices which are reachable from the source via an unsaturated path, it will define a cut. Of course, y is on the other side, otherwise we could have got an incrementing path already. So, this cut will be saturated by the flow in the sense that all outgoing edges are saturated and also all incoming edges are of 0 value. Therefore, this is the value of the flow is equal to the capacity of this cut, and that means that it is a minimum cut and the flow is a maximum flow, and then we have indeed achieved a max flow by that. So, this algorithm of pushing through incrementing paths until we cannot do any further will indeed achieve a maximum flow. So, we just will discuss how to implement this algorithm, that is called Ford-Fulkerson algorithm, in the next class. Thank you.